Hello, good afternoon. Okay, so exciting times. The final exam schedule has been posted, and we are not until, I want to say, April 28th. So I think it's the second to last day of the final exam period. So the final exam, I'm pretty sure, is on April 28th, and I think it's a late night exam. Let's see here. I'm gonna have to log in here. Yes, go for it. I put it at the very bottom here. Oh, not the very bottom. April 28th from 6 till 9 p.m. That's crazy. And of course, it's online. So from 6 to 9. And I can never remember if it's, yeah, you've got plenty of time to study, time to forget everything that you've learned too. You'll be busy with other things though, I'm sure of it. But so from 6 to 9, and I want to say it's PST, but now it might be PDT because we had daylight savings this weekend. And so I think it's called PDT technically, but of course, BC time. And it's online. We have to write it in that time frame, of course, so there's a lot less flexibility than what we have done for the test. And speaking of test one, you guys did so great, too well, in fact. So I'm gonna have to make it a little bit harder for next time. I think those definitions are really difficult, but you guys had no problem, I guess. They are just from the textbook. So to be fair, but great job. And I think I even have a little sticker for it. Whee! Great job on test number 1. Yeah, you just memorize it. So that's easy enough, right? So great job there. I'm happy with you guys having a good solid grade on one of your tests, and hopefully both of your tests, but at least one. It always feels nice to kind of have that booster. So really good job. And what else before we wanted to, I think that's it. I feel like there's something I'm forgetting. But anyways, here we go. So great job. Hey, that's a weird smiley face on test number 1. Woo. Okay, so we're going to start chapter 4. And chapter 4 is on regression, and my goal is to finish chapter 4 in this week, right? And so that means we're only going to have 2 days to talk about it. So I'm only going to be able to touch on the most important things, which means that, of course, I'm assuming that you're reading along and filling in the gaps with the textbook. So chapter 4 is on regression and prediction. Okay. So chapter 4, just so you can kind of keep them straight, chapter 4 is when we are trying to predict numerical data. Right. So when your Y variable, your outcome variable is numerical, then you're doing regression. Okay. And you're able to predict those values using regression. Now you've seen regression, so we're going to kind of float through it and just kind of highlight some things that we haven't seen yet. necessarily. Although you might be taking regression with Claude and then this week is going to be a snooze fest. That's okay. I'm okay with that. But one thing that I want to highlight is that in chapter 4, we're going to have numerical outcomes. So predicting numerical outcomes. Versus chapter 5, which I feel like is just classification, or what's the name of it? Yeah, it is just classification. Classification is when we're predicting categorical outcomes, and usually we're predicting binary outcomes, right? But in general, classification is the term that we use for when we're predicting categorical outcomes. Predicting categorical outcomes. Oops. Categorical outcomes. Now, the reason I highlight this is because, and I don't know how much else I can highlight this. The reason I highlight this is because it's really important for you to know the difference, but also I would argue that if you leave this program and you feel really confident with regression, so numerical outcomes, right? Predicting numerical outcomes, and classification, predicting categorical outcomes, then you are well prepared for the world, right? And so so these are going to be the kind of most important things that you're going to learn, in my opinion. Okay, and so everything else that we cover and that you see in your other courses are hopefully meant to just kind of help you get to this point where you feel really confident. Regression, so predicting numerical outcomes, and classification, predicting categorical outcomes, right? There's lots of other things that you can do, right? But they're all kind of getting you to that point. Okay, so chapter 4, of course, really important. And we did spend a fair amount of time at the beginning of the term kind of wrapping up Stat 230, because I didn't have enough time to talk about even simple regression in Stat 230, I felt like. So we've seen a lot of these concepts before, and now we're going to just run through it. And then in chapter 5, and let me just see what I meant to go to our Moodle page. Oh yeah, well, we didn't have class yesterday, but it was Pi Day, so I posted a little joke for Pi Day. It's my favorite Pi Day joke, even though it's not really, I don't know, Pi Day related, but it does have to do with pi. So I think it's really funny. And so we're only going to have this week in chapter 4, and then next week in chapter 5. And I am relying on the fact that you've seen a lot of this in Data Science 300, for example. I know that because I taught it last term. And then we're going to spend a week in chapter 6, and then we'll have test 2. So it's kind of coming up quickly. And I think I'll do the same thing where it's open all day and you can attempt it at any point. And then we'll finish off with chapter 7. Right. And then we've got our final exam. So between the 14th and the 28th, of course, sometime there, I want to schedule a final exam review session in case, and it'll be kind of drop in, but I'll schedule it closer to the final exam, so it'll be kind of fresh at least. But for now, let's get into chapter 4. Now, remember, a lot of this we've seen already, right? So here I'll kind of put brackets around that because we are getting into chapter 4. And so we have seen things like, so we have seen models like y hat is beta or b naught plus b1 x1, right? Where we've said things like, okay, well, this is my slope and this is my intercept. And this is my predicted value of y, predicted value of y. And you can use capital Y's or lowercase y's. I've noticed that the textbook likes to use capital Y's, whereas I personally am used to lowercase y's. But if you do kind of go on into higher level statistics, then you're going to use capital Y's. But in Stat 230, we use lowercase, but don't be thrown off by the capitals versus lowercase letters in this case. Hard to keep track of, okay? But in this case, you can use capitals or lowercase. Okay, so the predicted value of y, and we have some one predictor or explanatory variable. I just had like a moment where I thought I wasn't recording yet. We haven't done much, but tough to recap. Luckily I am, so it's good. Okay, so we're gonna start calling these predictors, and I'm gonna call this the predicted outcome. Okay, so y is gonna be some outcome. Yeah. So usually the point or the goal with regression is to predict a value of some outcome. And what I should have here is I should have little hats to denote that those are based off of the sample. Okay. And so we use regression. And in this case, this is what we call simple linear regression. Okay. Simple meaning there's only one predictor. So that's where the simple comes from. Okay. So we use regression to predict outcomes. Yeah. So this model that we use to predict these outcomes looks like it says but it says we use regression to predict outcomes. So typically that's what we're going to use regression for. There are a couple of other things, but in the end, we're going to use it to predict outcomes. Okay, and so so what that means is we use sample information to model this overall population model. Okay, so we use sample information to build a model of the population relationship. Which is actually going to be y is b naught plus b1 x1 plus the error term. And maybe, I can't remember if the text uses E or an epsilon. I think it uses an E. Just confirm here. Of course, yeah, E. It can be an epsilon though. I. Okay. Okay. So what this says is that this is the population relationship. So in the population, we understand that there's some error term, but when we're basing it off of a sample, we don't know what that error term is. And so our error is absorbed by these approximations of the coefficients, right? Or these estimates, these coefficient, the estimates of the coefficients. Okay. Okay. So we've seen simple linear regression. And so now what we're going to introduce is, of course, what if I have more than one predictor that I want to incorporate into my model? Okay. So what if I have more than one predictor? So X1, X2, X3, etc. I can have as many predictors as I want, and we'll talk about how many. But in general, you could include as many predictors as you want. So what if I have more than one predictor that I want to incorporate into my model? That I want to incorporate into my model. So for example, then my Y, my population model would look like B0 plus B1 X1 plus B2 X2 plus all the way up to some B, and I'm going to allow for P predictors, BP XP plus the error term. And maybe I won't, maybe I'll ditch the subscript I just for simplicity's sake. Okay, there are I's on there, but it's okay. Okay. So now I'm allowing for P predictors. Allowing for P predictors. Yeah. This is where it gets confusing because this is still a linear model, right? We're adding these values, so it's no longer a straight line, but how they are coming together is through a linear model, right? And so so this is a linear model. Okay, so since the predictors are added in the model, we call it a linear model. Okay. So as soon as we have multiple predictors, we call it a multiple linear regression. Okay. So multiple, multiple linear regression is when we have multiple predictors added in our model, right? So more than one predictor added to the model. Okay. Good. Okay. So these XIs, we're still going to call them predictors or features. Okay. So maybe I'll add that here, allowing for P predictors or features. Okay. I like to highlight that the P comes from predictors, but in data science, I guess it's pretty common that you call it features instead of predictors, but that's okay. Most people should know that they're synonyms, right? So you should be able to move kind of flexibly through them. So how do we fit a model to allow for these multiple features, right, or predictors? Well, we can fit a model and we use the same methods that we did for the simple linear regression, and we minimize the squares, the residual sum of squares. Okay, and so the same techniques are used, and we're not going to go into what that mechanism is, because of course R and Python both know what to do, but we should be aware of what they're doing, right? And so we fit the model by minimizing the residual sum of squares, Same as for a simple linear regression. Except now it's harder to visualize if I have anything more than two predictors, right, or two features, then I'm out of the XYZ plane, and it's really difficult for me to visualize this. But there still will be residuals, right? And so we can still square those residuals, and we can still add them up, and we can still minimize them, right? And so it's harder to visualize, and so that's why we start with a simple linear regression, and then we say, oh, and then we extend this to as many predictors as we want, but we can't visualize it anymore. Okay, so the same as for simple linear regression. Okay, so we fit the model by minimizing the residual sum of squares, and we find y hat is b naught hat plus b1 hat x1 plus b2 hat x2 plus all the way up to bp hat xp. Okay. And so these hats, these are estimates of the coefficients. Okay. When you fit the model using the LM command in R, for example, you'll have the option of telling it what to do with missing values. So missing values is not something that we are going to tackle here, because we're just going to take the very straightforward approach of just omitting anything with missing values. You can see how you would lose a lot of information that way, but we are also assuming that we're dealing with huge amounts of data. So then it shouldn't really matter in the end, right? And so our go-to is just going to be to omit the data, any missing data. However, there are techniques for dealing with missing data, right? So what are some of the things we could do? I could fill it in with the average value for that variable, right? Or I could do like a little bit of regression in between two values, right? Oh, well, if I saw this before and then I saw this, well, what if it's something in between the two, right? I could apply weights if I needed to. So there are many different ways that we could deal with missing data. So before we fit the model, or sorry, maybe I'll say as we fit the model, we need to decide what to do with missing data. We need to decide what to do with missing data. There are many techniques, right? Many sophisticated techniques. Imagine you've collected data that's very, very hard to come by, right? And you've managed to collect your sample size of let's say 35, and you had to spend a fortune to get there, right? And so you've got this very small data set, but you have some missing data, then you're not going to want to just delete those values, right? But in our case, we're dealing with huge amounts of data typically, and so we're just going to omit them. Okay. Since we will often have very large data sets, we will omit missing data. So we'll delete missing data, but we will omit missing data, so delete. We will omit missing data for simplicity. I will say as a follow-up, because I don't want you to be caught with your pants down and saying, oh, I'm just going to delete this data, because what if your boss says, whoa, 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 we spent a fortune trying to collect that data. You can't just delete it, a whole row of information, right? And so, oh, don't worry, I'll just delete it. No, right? There are cases where you can't afford to do that. And so I don't want you to think that that's the only thing that you're going to do. But for missing data, right, there are sophisticated techniques, and there are many different techniques. So there are many different techniques for dealing with missing data. Oh, could you use different methods? I would say yes. You would have to document it and declare why you used a different method for different variables. But there might be a reason for that. For example, if you have normally distributed data, then of course you know that, okay, then the mean is a good measure of center, right? But maybe you have another variable that's very skewed, then you would maybe use the median instead as a measure of center, right? So it's all going back to that nitty-gritty kind of stat 230 stuff, the groundwork that we laid, right? And so really good question. You can use different methods. I don't see why not. It's been a while since I've had to deal with missing data. But I would actually think that it would be fine and encouraged. But you would have to document what you did so that it's reproducible, right? So there are many different, great question. There are many different techniques for dealing with missing data, and they varying levels of sophistication. There are entire textbooks written about missing data. What should you do with missing data? So you could be a missing data expert, I guess, but usually we don't need to be. So there are many different techniques for dealing with missing data. And if your data set is small, you do not want to just omit your missing data, right? You will need to deal with your missing data. need to deal with your missing data. Right, instead of just removing missing values, or instead of removing observations with missing values. Observations with missing values. Think about how expensive that would be to your data, right? If you have a data set of, I would consider 1,000 kind of on the small side still, right? But what if you have 1,000 observations, but you also have 20 variables, right? That's 20 opportunities to have missing information, right? Everyone who's ever done a survey, right? You want to skip a question, that's missing data, right? So then all of a sudden that whole observation, we can't use it anymore if we're removing those data points, right? So if you want to use all the other stuff, the good stuff in there, then you have to deal with those. Okay, but it's kind of a small sample problem, which is where a lot of these techniques came from initially, right? Because we faced the problem of small data sets. We've seen that already. Okay, so if I've built this model, right? So as you fit this model, then in R, you would just tell it, I think it's NA omit equals true or something like that. It's really easy to tell it to omit data. I think, so in the LM command, oops, shouldn't do it, all cursive. Y tilde x1 plus x2 plus x3. You might do, I think it's NA dot omit equals true, but I can't remember off the top of my head. I'm just gonna, I think they mentioned it in the textbook, so let me just have a look here. If I can find it quickly. Oh, NA dot action equals NA dot omit. Haha, I was way off. Well, not really. NA dot action equals NA dot omit. Okay, and so I guess I should close my brackets. Got a bracket. Okay, so that tells me that there are other actions that I could take, but for removing the missing data, you're going to use the NA.omit. Something tells me NA.omit equals true is also going to work, but I don't know. Okay, so once you've run your model, and in the lab we'll see it because it's kind of hard to switch back and forth between the screens here. So we'll run a linear model, and I'm confident that you've already seen it, and so that's why I'm kind of skipping it for now. But once you've run your model, then what do we need to do? We need to interpret our coefficients, right? So once we have run the model, oops. Once we have run the model, we need to interpret the coefficients. In the simple linear regression case, right, we know how to interpret those coefficients, right? And so in simple linear regression, we had y hat is b naught hat plus b1 hat x1. Okay, so where b naught hat is the y-intercept. And what is that? The y-intercept, or b naught hat, is the predicted value of y when x is 0. The predicted value of y when x, or x1 in this case, and I'll add that to my brackets here, or x1 is 0. What's my b1 hat? My b1 hat is my slope. The slope says that for each unit increase in x, or x1 in this case, but generically, if we only have one x, then I would just say x. It's not until I have multiples that I need to distinguish between them. But for each unit increase in x, the slope is the increase in the predicted value of y. Okay. For each unit increase in x, right, or x1 in this case, we expect to see a slope increase in the predicted value of y. We expect to see a slope increase in the predicted value of y. Remember, our goal is to predict the outcome, right? Predict the value of y. So it is really important that we're able to interpret these coefficients that help us predict y, right? So it's really important that you can't just predict y, you have to be able to say what goes into predicting y, right? And so that's going to be key. Now, if I have, so in multiple linear regression, my model might look something like this, right? I have y hat equals b naught hat plus b1 hat x1 plus b2 hat x2 all the way up to bp hat xp, allowing for p predictors. Usually, you should stick to kind of less than 10 predictors. It gets a little crazy otherwise. I just want to match the, okay. So the b naught hat, the interpretation is the same. Okay, so b naught hat is the predicted value of y when x or all the other x's are 0. Okay. The predicted value of y when all x's are 0. Oops. When all x's, and let's say xi's, are 0. Okay. Now, the slope coefficients are a little bit trickier, right? Because we have all these different predictors going into our model, but how we interpret each coefficient assumes that all the other things stay the same, right? So you can only let one thing change at a time in order to interpret these coefficients. And so beta I, or bi hat, I shouldn't say beta, because that's for the population, and also I haven't been using betas, but could be. So bi hat is to denote B1, B2, B3, B4, okay, all the way up to BP hat, is the predicted value of Y hat changes by this amount, right, for each increase in the respective X, okay, assuming everything else is held constant. Okay, and so the predicted value, let's write that down. The predicted value of Y changes by the coefficient, changes by the coefficient beta, or BI hat. I keep saying beta. Technically it is betas, but we're not using that notation. If you want to, that's fine, but I should stop saying it. Okay, the predicted value of Y changes by the coefficient BI hat for each unit increase, right? So it does have that same ring to it as a single X, right? But a single X doesn't have to worry about anything else varying. The only thing that could change is that X, right? And so for each unit change, and I would say increase, but in Xi, assuming all other variables remain the same. Assuming all the other variables xk, right, for k not equal to I, of course, remain the same. Right, so they can't change. We can only interpret one coefficient at a time, right? Okay, so now we're going to pretend that we have some model, right? And there are lots of different ways that we could arrive at that model, but first we need to talk about, so how can I assess the model? How do I know if I have a good model or not? Okay. So once I have built the model, I need to be able to determine if it's a good model, right? I need to be able to determine if it is a good model. And so we call that assessing the model. Assessing the model. There are lots of ways that we can do it, and a lot of time over the years has been spent trying to figure out what the best model is, right? What makes a good model? It means that our predictions are good, right? And so a good model why do we want a good model? Well, let's think about it, right? A good model yields reliable predictions, okay? Yields reliable predictions. So of course, we want to pick the best model. And there are many kind of metrics that we can use to assess the model. There are many techniques or many metrics we could use to determine or to assess a model. There are many metrics we could use to assess the model, to assess a model, I should say. And maybe I'll put a little space here. I put the assessing the model, I put it because I had a page break here, so that's why it looks all squished, but otherwise it would be nicely spaced out. But so there are many metrics that we could use to assess a model. Now, the main one is going to be the root mean squared error. The root mean squared error. Root mean squared error. Okay. And how we calculate that is we've already seen residuals, and so it does leverage residuals, but it also does some other stuff to it. Okay, and so it's going to be the sum from I equals 1 to n. So each data point, right, our sample size is n, so from 1 to n, so considering all our data points, we're going to be able to calculate some residual, which is the observed minus the predicted, square it. Okay, so this, remember, is your residual. You square your residual and then you add those up. And then for the root mean squared error, so we've got the squared error component, okay? To get the mean, I have to add them all up and divide by n, right? That's how many units I've included in my sum, so I have to divide by n and the root, right? So kind of reading from the outside in, so the root and then the mean comes from summing the squared errors. Okay. The root mean squared error is kind of the go-to metric that we would use. Okay, and so this is the go-to metric. However, the standard R output has the root squared error. So not the mean, but the squared error. And so it's going to have the root mean squared error, but it's not going to be in that default output. Okay, so RMSE will be one of the most common metrics, to use. Common metrics used to assess a model. In fact, what are you trying to achieve? Are you trying to maximize or minimize the root mean squared error? Well, if you want your predictions to be reliable, then your residuals would be small, right? If I square small values, it stays smaller than it would have if this was large. Add those up, I'm still getting a small number. And if I divide by n, it's a small number. And if I take the square root, it's a small number. So I'm trying to minimize the root mean squared error. Want to minimize, and let me just, want to minimize the root mean squared error. Okay. The default output in R, gives the root squared error so RSE instead of RMSE. Yeah, so a smaller root mean squared error is a better model. So if you have two models that you're comparing, you would pick the one with the smallest RMSE. And we'll have some other metrics to compare as well. R squared, for example. So the default output in R gives the root squared error instead of RMSE. Okay, so the root squared error. Yeah, so R squared, you want to increase your R squared. So you want to have, so this is where it gets tricky, right? You want to minimize your RMSE, or if you're looking at your R squared, you would want to maximize your R squared, right? And then we're also going to look at a Keki's information criterion, or AIC, which you also want to minimize. So it depends on what it's considering. All right, so you got to keep your eye on the ball. So the RSE is very similar. So I'll start out by writing the summation I equals 1 to n. It still considers the residuals squared. Okay. But instead of taking the mean, we divide by n minus p minus 1, and then we take the square root. Now, this n minus p minus 1 is actually your degrees of freedom. Degrees of freedom. Now, what it does is it penalizes you for having too many predictors. And that's kind of a common thing that we do, is we are always striving for the simplest model possible, right? For interpretation reasons, for reproducibility reasons, right? And so we're always striving for the simplest model. And so the RSE penalizes you for having too many predictors. Okay? Because if I have one predictor, then I have n minus 1 minus 1, so n minus 2, right? So I'm dividing by n minus 2. Whereas if I have 10 predictors, right, then I have n minus 10 minus 1, and so now I have n minus 11 as my divisor, right? So now I'm dividing by a smaller number, right, which gives me a larger number, but we're trying to minimize this thing, right? And so all the formulas tell you what the goal is, but sometimes it's hard to get there on your own. So here, RSE penalizes models with too many predictors, or I should just say with many predictors. P is the number of predictors. One thing that I will say is if you have a large sample size, right? So let's say you have a sample size of 1 million, and then the difference between 1 million minus, or just 1 million versus 1 million minus 11, that difference is not significant, right? So, so for large data sets, the RSE is basically the same as the RMSE, right? So for large data sets, right, n is large, RMSE is basically the same as the RSE. RMSE will be similar to RSE, right? The difference between n and n minus p minus 1 is not huge, right? When you're dealing with a huge value of n. Okay. So Another metric we could use, another metric we could use is R squared. Now, instead of talking about what R squared, the formula for R squared is, because it's the correlation squared, and we could, but I don't want to, because you should not be able to. So as a rule, okay, so the question was, is there a possibility of getting a denominator of 0? Now, of course, in this case, no, there's no possibility of that. However, if you have this oblong data set, right, then your n is going to be smaller than the possible number of predictors. But as a rule, you never want to have more predictors than you have observations. So here I'll add that because it's a good thing to note, right? We can't divide by 0. That's illegal math. So just as a quick note, n should always be larger than p in your data set. If it's not, then you can't include more p's than you have observations, right? So even if you have more predictors to choose from, you can't include them all in your model. So so that's good, all right? But you always want to have a data set that's either square, but that's kind of living on the edge, or rectangular going down, right? More data points than you have predictors. Good. Okay. R squared, we've seen before, we've seen as our, oops, usually it clicks there. This is the only metric that we use to gauge our models in Stat 230. We said, okay, a higher R squared is good, right? And then I made you memorize the definition of R squared. So R squared is the percentage of variability in the predicted value of y, or in y, explained by the least squares regression line on x. Explained by the least squares regression line okay. So that's in general, the definition of R squared is the percentage of variability in y that's explained by this model. Now, of course, you want to be able to explain as much of that variability as you can, right? So the goal here is to maximize R squared. Oops. Maximize R squared. Okay. And the formula for R squared is in the textbook, but because it incorporates a couple of different things, and it doesn't really matter because our output includes the R squared. So I'm going to skip it, but you can look at it if you want to. So the goal is to maximize R squared, and our output, confusing, right? R squared is different from R, although obviously there's a relationship there. Correlation is R. I know. So is the adjusted R squared, which again, the adjusted R squared penalizes you for having too many predictors in your model. Okay. So our output our output includes the adjusted R squared which is the R squared, so you're still trying to maximize it, which is R squared, right? So the goal is to maximize it, which is R squared, but penalized for increasing your number of predictors, but penalizes the model for including too many predictors, or maybe I'll just say many predictors. I don't want to talk about too many because then there's a certain amount that is allowed, but as you increase your number of predictors, your R squared, adjusted R squared, is going to start to be penalized. Okay. I'm going to skip that for just a little bit here. Another metric we could use, and I don't know why. Sorry, I've made notes here. And I remember seeing something that I wanted to talk. Oh, here it is. Okay. So another metric we can consider is the AIC, which is, I want to say AKKs, but I don't want to screw this up either. Yeah. AKKs information criterion. Okay. Which is, so the AIC is 2P, where P is still the number of predictors. So you can see there's a lot of fuss about the number of predictors that you have in your model. In fact, 2P plus N, which is your sample size, times the log of the RSS, the residual sum of squares, residual sum of squares, which we've seen, right? This is the residual sum of squares. So it's part of the RSE, but now we're not taking the square root or anything, and we're taking the RSS, the residual sum of squares, divided by N, and then we're taking the log of it, right? But we're penalized by a factor of 2P, right? So we're kind of amplifying the number of predictors. And so the goal here, because that's what I find the trickiest, it's not hard to find these values once you have the output, right? The hard part is figuring out, okay, what am I looking for again, right? Does it have to be maximized or minimized, or do I have to find some happy medium here? So the goal is to minimize the AIC. So the AIC is another common criterion that we use for just picking a model, right? What's a good model, right? A good model minimizes the AIC, and notice that incorporate some of that same information. So they all hinge on the residuals in some way, right? And I'm sure there are methods that don't, but the ones that we use all hinge on the residuals. And in fact, the residual sum of squares. There are other metrics. Just so you're not thinking that these are the only ones. There's the Bayesian. Oops, I've forgotten an E in there. The Bayesian information criterion. Which is the BIC. There's Mallow's CP and others. Not going to consider those, but they are all things that you could look into if you're interested, right? And things that we could consider. But for simplicity's sake, let's focus on the RSE or the RMSE, the R squared or the adjusted R squared, and also the AIC, so the Akicki's information criteria. Okay. And we can consider a combination of these metrics. Okay, now let's see here. Most of these metrics penalize a model with too many predictors or with many predictors. Most of these metrics penalize a model with many metrics, or sorry, with many predictors. Okay. And that's because our goal is to always pick the simplest model, right? And so that is because we always want to pick the simplest model. There are a couple of reasons, but some main reasons include interpretation, right? It gives us an easier model to interpret, right? So it's easier to interpret, but also it's easier to reproduce, right? If you don't have to collect all information on those predictors, on a ton of predictors, if you know that your model does a good job predicting values with just these 3 predictors, for example, then in the future, you only need to collect that information, right? And so it's more reproducible. Okay. So those are some of the reasons. So the simpler model is the better model, and that's what we call Occam's razor. Doesn't matter, but it's just kind of fun. They've included it in the textbook, so why not? I'm not going to write it down though. It's not important, although it's kind of like a fun fact. Okay, so we can compare the overall models, but we can also compare each of the predictors inside our model. So we can compare overall models using the metrics above. But we can also compare predictors inside each model. But we can also compare predictors inside each model. Okay, so each each coefficient is going to have, so each coefficient is an estimate. So in our model, we have estimates of each coefficient. We have estimates of each coefficient. Okay. Just like the mean has the standard error of the mean, right? And the proportion has a standard error, right? We're also going to have, so each estimate has some standard error. So we have estimates of each coefficient, which is beta or B, and I think I was using I before. I'll use J. No, I should stay same. I shouldn't have used I earlier because I is to denote each observation, but that's okay. BI hat. So each estimate, just like before, is going to have some distribution. And so it's going to have some standard error, right? And so each estimate has some standard error. And maybe what I'll say is not that each estimate has a sampling distribution, just to kind of draw the connection between stat 230 and here. So each estimate has a sampling distribution. So it will have a standard error. So the standard error of BI hat, which we can use, right? And what I'm going to tell you is that it's going to follow a t distribution, and it's going to have some degrees of freedom, but we don't need to worry about that. So the default R output includes the estimate. It includes the standard error of each estimate. It includes the t value, right? For each estimate, and it includes a p-value as well. Okay, we're not going to need to focus too much on what these mean quite yet, in fact, ever. But we can calculate, so the default R output includes the estimate BI hat. It includes the standard error of BI hat. It includes T, which is your BI hat over the standard error of BI hat. So how far is it from 0 is what it's technically doing. Like I said, this is me getting all statsy and not really focusing on what we need here. But it's fun, right? So what am I testing? How far is my estimate from 0? 0 meaning 0 says that it doesn't contribute, that predictor doesn't contribute at all, right? And so, and then it gives us the probability, whoops. The probability of being greater than the absolute value of t, which is your p-value. It's your two-sided p-value, and that's good, but let's ignore that for now. Okay, and so this p-value helps us select predictors. If we're just kind of going rogue, and we'll develop some ways that we can kind of work through these models, but and select predictors. And so the p-value, we can use the p-values to select predictors that contribute significantly to the model, right? So my p-value has to be significant, so less than 0.05 typically, right? So we can use the p-values to select predictors that contribute significantly to the model. Oh my gosh, what time is it? I only have 2 more minutes. I think. Let me just confirm here. Oh my gosh. I do. Time flies when you're having fun. Maybe that's actually a good place to end for today, since I'm not going to be able to tackle another concept in only 1 minute left. So I think that's where we'll end it today. And we'll pick up here on Thursday. If you have any questions, let me know. Otherwise, I will see you then. Stop this recording here.